Okay, welcome back. And let's try to summarize if learning is feasible or not, given whatever theory we've built until now. So, is learning feasible with, of course, a finite hypothesis, which is H? Okay, so the question has been answered in a certain way, but now we are trying to summarize that and put things in perspective. So, a short answer to that question is yes, learning is feasible, right? Provided we accept a two-step approach. And what was that two-step approach? The two-step approach was first E out, and this is determined theoretically. So if E out is almost equal to E in of G, and this needs to be done theoretically and with a high probability. So let me write down here, this has to be done theoretically, and we should be able to say like with high probability. We are not 100% sure, but with high probability. So with high probability, if we can establish this, and then provided we have E of n almost equals to 0. Now we can verify the second condition by running the learning algorithm and computing E in, which is like the in-sample error on G, right? Okay. Now there are certain conditions that underlie these this like two-step process that underlies that. And in order to accomplish like this two-step process, there are certain conditions that we need to have. Like those conditions need to hold if we want this to happen. What are those conditions? So let me write those first. Conditions. Okay, so the first one is, and we've talked about it like multiple times now, that we have to fix the hypothesis set ahead of time in order to guarantee that we will like have this two-step process as valid, right? So the first condition here is that fix H ahead of time, or like ahead of seeing the data at least. So that this also implies that my final hypothesis actually belongs to the hypothesis set that I selected initially, right? So this is the first condition. Now, the second condition is that for step 1 to be true, which is like this thing here, for step 1 to be true, the data should be independent and identically distributed according to some probability distribution. And there is no constraint on which probability distribution it's going to be, but it should be random. That means IID, right? So the second condition is data must be IID, right? Maybe from some probability distribution P of X. And again, there's no restriction to what that is going to be. The third condition is that this E out of G is for a random test point that came from like P of X. So basically what we're trying to say is that the test point also comes from the same distribution as this one, right? So maybe writing that this error, the out of sample error, is calculated, or obviously it's not directly calculated, but we kind of get the information from the two-step process, right? But that is for that random test point that also came from, so X is, let's say, the random test point, and this also comes from the same distribution, comes from P of X, which is like the same thing as this. Okay, so as long as these three conditions hold, then we can definitely say yes, learning is feasible via the two-step process, right? Now, thinking a little bit more about what's going on in terms of the error process, and by the way, this is kind of telling us that like both the test and the training came from the same bin, if you remember the bin model. Okay, so going back to is learning feasible, the first point was yes, provided we accept a two-step approach. The second thing is let's assume that we are doing some like some kind of a learning process, and we get like, let's say, 60% accuracy. In another experiment, we get a 50% accuracy, and so on, right? So I don't know, by accuracy I mean the error, right? Let's say the E in or the in sample error can be like really bad in certain situations, is what I'm trying to say. So this condition, the first condition, actually also wants us to ensure that no matter what we get, right, although it's considered a failure in terms of the learning problem and in terms of the learning process as a whole, we have to accept it, right? We have to accept it as it is. And that leads us to the point B, actually. So this is point A. That leads us to point B. Let me write it down. H is possible to fail. So whatever H is has a possibility. Maybe I should write has a possibility to fail. And we need to accept this, right? Basically, this hypothesis provides a stopping criteria. And after failing, you will like try another set, obviously, right? Because if you got a really bad outcome, you feel that this wasn't the hypothesis set that you really wanted, or you eventually end up because the target function was such and so on. Like there could be multiple reasons for that, but the important point here that I'm trying to make is that we need to accept and we need to incorporate that in our model that this failure is absolutely possible. Okay, so having said that, these are the two, basically this A and B, A plus B, it actually summarizes the fact that learning is feasible. Okay, so having said that, whatever we have, like our entire learning approach, we want to make sure that this approach is general, which means that it applies to every machine learning problem out there. Okay, so whether that is true or not, and well, again, the answer to that question is that our learning approach is indeed general because it applies, let me write that down as well, it applies to any target function f. Okay, that's awesome because I don't know what my problem domain is going to be. I don't know what kind of a target function there will be given to me if I'm trying to predict things, right? But this entire learning approach, this entire theory applies to any target function. And the second point here is that, and why, and basically we are trying to list out the different components of why, like what makes this learning approach general. Okay, so the second point is that it applies to any probability distribution function. As I said, my data has to come from a certain probability distribution function. There is no restriction on what it's going to be. So it applies to any P of X. And this approach also applies to any hypothesis set H. So that's even better. I can come up with all sorts of functions, right? So it applies to any hypothesis set H. For example, it could be like PLA, neural network, support vector machines, I don't know, whatever. But this theory will apply to any of them, all of them, right? And the fourth point, which is again extremely important, is that it applies to any learning algorithm. So basically, whatever the sequence of steps you follow in order to pick the final hypothesis G, whatever the algorithm was there, this theory will apply to that, right? So applies to any learning algorithm. Okay. The only thing, like again, I would like to like reiterate what we said earlier. So the only thing that really matters here, that all our conditions that we specified earlier, right? So all our conditions must hold. That's the important part. Otherwise, our learning approach, our entire theory that we built until now is applicable, it's general to all of these, right? It applies to any target function, any probability distribution, any hypothesis set, any learning algorithm. All conditions, and by conditions, I mean these three conditions. They need to apply fixed hypotheses ahead of time, data must be IID, and then the training and the test must come from the same distribution, right? Basically the idea of same bin, as I said. Okay, so having said that, we have established that our theory is general and yes, learning is feasible based on certain criteria. Okay, so now we move on to discussing the target function, because eventually everything that we've done until now and we want to do in future ends up at being able to predict the target function or the values of certain like data points and depending on the target function, right? Okay, we have talked about a little bit about the complexity of the target function. So I will repeat a little bit of that more in the context of what we know now. So complexity of the target function. If you don't remember the definition, it was how hard it is to learn a certain function. So the harder it is to learn a target function, the more complex it is considered. Okay, so this is the first one. The second thing is about the target function. There could be noisy target functions. What is this noisy f? Well, think about, until now we've said that f is deterministic. It's some deterministic function, but f could be stochastic, right? So basically it has noise in it. That's what this is telling us. What if like there were certain measurement errors in my data? So what if like my f is non-deterministic? So then what? So then the target function is considered to be a noisy target function. Okay. The third thing that's important in terms of the target function is error. Now we've talked about error until now, and if you think about it, we've talked actually about the probability of error. So now, do we care only about the probability of error, or is there something else that we want to add to our definition of error as a whole, right? Now, all these three important things, they do not impact theory as much, but answering these questions is important because now we are moving towards the practical side of things, right? So practice. So these things are important in terms of like when we are actually implementing things and when we'll actually do things with real world data. So that becomes important. But regardless, right, the theory will hold as much as it's been holding until now. The theory still holds even if we are moving towards practice. Okay, let me quickly review because we have talked a little bit about complexity of the target function. But again, as I said, if you remember the Hofding's inequality, it wasn't like quite evident what role f has to play. But if you think about it, the data actually on which I'm like training my algorithm, the data on which I'm calculating the errors, all of that is coming from some distribution which is like underlying f, which has like underlying f in it. So basically, if I have a complex, if I have a complex f, then what happens? Well, obviously it's not evident, but I know a complex f is hard to learn, right? So it will be hard to learn. That's a given. So in order for me, remember the two-step process. So in order for me to get an E in almost equal to 0, right? I need a larger h, right? My h should go up. The number of hypotheses should go up. So it has to be bigger. And in order to be able to learn a more complex target function, I should have a bigger hypothesis set. Now, this means higher error bar, if you remember, right? So the error bar, if you remember, and we later denoted it by omega, and it was a function of my hypothesis and my n, right? And given if like n was a constant, wasn't changing, the sample size wasn't changing, then we figured that this is going to go up as well if my h increases, right? And also if you remember, like in the definition of omega, the like hypotheses set, the cardinality of the hypothesis set was in the numerator, and then there was a square root, of course, and then n was somewhere here in the denominator, right? So in order to counteract this like effect of increased hypotheses because the complexity of f is high, and so the increased error bar and e out is deviating more from e in, right? All that we talked about earlier. So in order to counteract this effect on the hypothesis set being getting bigger and bigger, I can choose a big N, right? So if I choose a big N, then what happens, right? It seems to be the only way out where theoretically, in order to get my E in very close to E out, which was definitely not the case when the hypothesis set was getting bigger and bigger, but we can counteract that if we have a large or a big N, right? We can somehow reduce the impact of H getting bigger and bigger, right? So if h is getting bigger and this is also getting bigger, there is a way to keep this in control and so that E in will not deviate too much from E out. So basically what this complexity of the target function is saying is that it's harder to learn a more complex target function because we need more data. Because we need more data to learn that, right? So in like, if you think about like how we started with the more number of hypotheses, but then we thought that the complexity is more, so my E out will deviate more from E in, but eventually we arrived at the fact that we can control that if we have more data. And the fact that we need more data is what is making it complex from my perspective of like implementing things. Okay, so that was about the complexity of the target function. What if we have a noisy target function? As I said, measurement errors. For example, I have this credit card application process, approval process. I have the exact same data for two different customers, but one was approved and one was declined, right? So that could have been there. So that's what a noisy target does. Basically, you can have in your input space, you can have the same X, right? My input is same, but I can have like for some cases it could be +1, and for some cases it could be -1. And remember, the data is coming from the same distribution essentially. So basically, we can think of the f or the target function being like noisy, right? So that's what noisy means. So this is the scenario where you can say the target function is noisy. But basically, if you think about it, my target function is nothing but a distribution over my outputs. So what's happening here is that it is coming from a distribution, of course, as we said earlier. And so y given x, right? So this f is exactly the distribution function over my set of outputs. Now, because the noise is both in sample and out of sample, therefore theory will still follow, right? Although the case might be that my E in when I'm trying to calculate will not be as close to 0 as I would like. And then E out will also deviate more because we just know why, right? So then that's the issue with the noisy target. But anyways, the theory applies, and this is what the noisy target looks like. Basically, I'm including that distribution that includes the noise, right? So I'm getting the data from the distribution that has that noise. So that's what a noisy target function means. And then finally coming to the error part. So what I'll do is I'll end this video here, and in the next video we'll talk about the error of a target function and how to quantify that error in terms of like implementation. Okay.